This is a video about momentum and impulse. Momentum is a measure of how hard it is to change the velocity of an object. We measure momentum with this equation, P equals mv, where m represents the mass and v is the velocity. So therefore, the unit for it is kilograms times meters per second. In this really simple equation, we're asked what is the momentum of a 2 kilogram object moving 3 meters per second. So in our really simple equation for momentum, we just take the mass and multiply it times the velocity. So that would be the 2 kilograms times the 3 meters per second, and that would give us 6 kilogram meters per second. Another topic we will learn is impulse. Impulse is the product of the force applied on an object over time. Impulse is the force, the symbol for it is J. The equation for it is force times time, with the units being Newton seconds. This example asks, or it says, the 2 kilogram object is moving 3 meters per second, that is moving 3 meters per second, experiences a 4 Newton force for a 0.25 second duration. What impulse does it experience? So with our equation of impulse is equal to force times time, we would simply take 4 newtons, multiply it times that 0.25 second duration in which it's experiencing that force, and we would get 1 Newton seconds. We're going to find out later that there's actually a relationship between kilogram meters per second and Newton seconds, between those two sets of units. The reason for that relationship is the impulse momentum theorem. It tells us that the change in momentum, not just the momentum, but the change in momentum is equal to the impulse that an object experiences. So this is the equation that states that the impulse, which is the force times the time, is equal to the change in momentum. And we will look at a very specific example, this example, in class. We'll also look at this example in class that relates the force versus time graph and how impulse and the change in momentum are related in graphs. Now, we're going to find that a very, very important topic in physics is a conservation momentum. And just like in a closed system, when we were talking about the energy model, in a closed system, energy is conserved. Well, also in a closed system, momentum is conserved. Now, we have to understand that momentum is a completely different quantity than is energy. Okay? The conservation of linear momentum is what we're going to focus on now. And we're going to find out that there are a range of types of collisions in which we will apply the conservation of linear momentum. We will find that there are completely elastic collisions, and by definition, kinetic energy is conserved in completely elastic collisions. We'll also look at the other end of the range or spectrum, where we have completely inelastic collisions. And in inelastic collisions, we'll find that kinetic energy is not conserved and that the objects stick together. In the real world, most collisions are actually somewhere in between. They're partially inelastic or partially elastic. Now, the strategy we should use for all collisions is this. First of all, let's look around the problem and see if it says elastic. If it says it's elastic, or that it says that kinetic energy is conserved, then let's start off with this equation, saying that by definition, if it's elastic, the kinetic energy is conserved. If it's a two-body collision, we should plug in the 1/2 mv squared for each of the two bodies and recognize that the kinetic energy of each body before the collision should equal the kinetic energy of each body after the collision. In conjunction with the conservation of kinetic energy, we should also use the conservation of momentum. Now, for all other problems that are not elastic collisions, we would use the conservation of momentum equation. So for elastic collisions, we're going to use that equation in conjunction with that equation. For all other collisions, as long as it's a closed system, we will use conservation of momentum. All right, now here are some types of collisions. Now these types of collisions, we will always use conservation of momentum as our most important equation, that equation there. Now I've come up with these terms. I came up with this term of regular collisions. A regular two-body collision would use that type of equation there. An inelastic collision would be a different version of our two-body collision, what it would look like that. An explosion collision, we would use this, and we'll talk later about moving explosions. But what's most important is all of these types of collisions all stem, or the solution, I should say, of those types of collisions should stem from the conservation of momentum equation. This is the most important equation. So here is the momentum method. This is the method I'd like for you to follow to maximize your credit when solving momentum problems. Draw a labeled picture first. Draw before and after motion maps. Write a momentum conservation like momentum is conserved. Include, if it's true, the term inelastic collision or elastic collision, and make sure you state why. If it's an elastic collision, say kinetic energy is conserved. If it's an inelastic collision, say that the objects stick together. Also, make sure you always write the conservation of momentum equation, that the initial momentum equals the final momentum. Write the specific equation, in other words, plug in the masses and the velocities. Make sure to substitute the correct values and then solve, and your final answer should include the correct units. Now, let's apply the momentum method in what I call a regular collision. In this example, before the collision, a bumper car, which we'll call bumper car number 1, which has a mass of 100 kilograms and it's moving 2 meters per second to the right, runs into bumper car number 2, which is 90 kilograms and moving 1 meter per second to the left. After the collision, bumper car number 1 moves to the right with a velocity of 0.1 meter per second, and we're asked, what is the velocity of bumper car number 2 after the collision? All right, so the first step is to make sure we draw our labeled picture. So there's our labeled picture. Now your picture doesn't have to be as detailed as this, but you get the idea. The next step is to draw the before and after motion maps. So the before motion map would look like that, and the after motion map would look like that. With us trying to figure out what's happening with the motion map of bumper car number 2. Then we need to make an energy statement. And in this case, we will say momentum is conserved. Actually, in all cases, as long as the system is closed, we will say the momentum is conserved. We'll write the momentum equation. Now, we skipped step 4 where we say whether it's elastic or inelastic, because in this setup it's actually partially elastic or partially inelastic. So we skip that step. Only when we know for sure that kinetic energy is conserved or the objects stick together do we say that it's elastic or inelastic. Then what we do is we write out, we plug in the mass times velocities for each object. So this is m1 v1 for this object, m2 v2 for that object before the collision. This is M1V1 for bumper car number 1 after the collision, M2V2 for bumper car number 2 after the collision. Now, you may not be able to see this in the video, but there are little lines there that denote that that's V1 prime and V2 prime for the velocities after the collisions, right? Notice that the masses before the collision are the same as the masses after the collision. So then our next step is to include all of the correct substitutions. So it's a 100 kilogram cart moving 2 meters per second. It's important to have the signs because momentum and impulse, momentum in general is a vector, and as an aside, impulse is also a vector. So for our momentums, it's important to include the directions. So for the velocity, the bumper car number 1 is going to the right, 2 meters per second, so that's why we include that positive sign. Bumper car number 2 before the collision is going in the opposite direction or to the left, so we're going to include a negative sign for it. And we need to make sure we've got the right masses before the collision. After the collision, we find that the 100 kilogram cart is still moving to the right, but now it's going 0.1 meter per second to the right. And then we're asked to solve for V2. So at this point, we're simply just doing our math. The 100 kilograms times 2 becomes 200 kilogram meters per second. The 90 kilograms times negative 1 becomes negative 90 kilogram meters per second. The 100 kilograms times 0.1 becomes 10 kilogram meters per second on the right-hand side of the equation. And again, we're looking for V2. So in our next step, we add the 200 and negative 90 to get 110 kilogram meters per second. On the right-hand side, we still have 10 kilogram meters per second plus 90 kilograms times V2 prime. Then we subtract the 10 kilograms from both sides, so we get 100 kilogram meters per second on this side, and we still have our 90 kilograms times V2. We divide both sides by 90 kilograms, and we end up with a positive 1.11 meter per second. So we actually find that this car will move 1.11 meters per second in this direction. So to complete the motion map, we would show our velocity arrows going in that direction. And these examples, this inelastic collision, we will complete in class along with this explosion collision.